Welcome to this presentation. In this video, I'll be walking you through the model architecture implemented in our FreeScopes platform, highlighting each component and its role in achieving accurate target detection, localization, and classification. Let's start with the first figure, which provides an overview of the connected model in our FreeScopes platform. The workflow starts with the Load Input Data block. This block is critical for loading the recorded radar data, along with the position labels that indicate where targets are located. This initial step sets the stage for the rest of the pipeline by ensuring that both the input data and labels are properly formatted and ready for processing. Next, the data flows into the Pre-Process Input Data block, where significant pre-processing is performed. This step normalizes the IQ data generated by the radar simulator, ensuring that the input data is scaled appropriately for the model to process efficiently. Additionally, the position labels undergo transformation into Gaussian labels, which smooth out the target location information. By representing position labels as Gaussian distributions, we make it easier for the model to learn where the target is positioned in the data. This is especially important for enhancing the accuracy of the localization task. Once pre-processing is complete, the data is fed into the model, which is built using a structured sequence of blocks. The first stage in the model is a 1D convolutional block, which extracts relevant spatial features from the input data. This block uses a convolutional kernel to process the data and identify patterns that can later be used for classification and localization. The output of the conv1D block is passed into the flatten block, which reshapes the data into a format suitable for the dense layers. From the flatten block, the data moves into a dense block, where higher-level representations of the features are learned. At this point, the model splits into two parallel branches, each responsible for a specific task. The first branch leads to another dense block, which further processes the data. The output of this block is then passed to the position output block, which generates a 400-element output. These 400 elements correspond to the positional resolution of 0.05 meters, covering a range of 20 meters. The softmax activation function used in this block ensures that the output represents a probability distribution across all positions. When a target is present, the softmax output spikes close to 1 at the corresponding position, indicating the exact location of the target. The second branch also flows through a dense block, which connects to the classification output block. This block generates a 3-element output corresponding to the 3 classification classes. Class 0. No target present. Class 1. Target with low radar cross-section, RCS. Class 2. Target with high RCS. Like the position output block, the classification output block also uses a softmax activation function, ensuring the outputs represent probabilities for each class. Finally, the outputs from both branches are passed into the model compile block, where the model is prepared for training, and then into the train model block, where the training process takes place. Now, let's take a closer look at the third figure, which provides a detailed breakdown of the model architecture. The conv1D block is defined with a kernel size of 1 by 1 by 64, meaning it processes one-dimensional data with 64 filters. It also includes 64 biases, and the output is activated using a ReLU activation function, which introduces non-linearity to the model and helps it learn complex patterns. The next block is the flatten block, which reshapes the data into a 1D vector, preparing it for the dense layers. The dense 3 block contains 512 neurons and 512 biases, using another ReLU activation function to learn high-level features. This dense layer serves as a critical bridge between feature extraction and the specialized branches of the model. From dense 3, the flow splits into the 2 previously mentioned branches. The first branch passes through dense 5, which has 64 neurons and a ReLU activation function. This is followed by the position output dense block, which has 400 neurons, corresponding to the positional resolution of the radar data. The softmax activation function in this block ensures that the output represents a probability distribution over the 400 positions. The range of 20 meters with a resolution of 0.05 meters makes this output ideal for accurately localizing targets. When a target is present in the data, the softmax output produces a sharp peak close to a probability of 1 at the corresponding position. effectively pinpointing the target. The second branch passes through DENS4, which also has 64 neurons and a ReLU activation function. This leads to the classification output DENS block, which has 3 neurons, corresponding to the 3 classification categories. The softmax activation function ensures that the model outputs probabilities for each class, enabling it to differentiate between the presence of a high RCS target, a low RCS target, or no target at all. Together, these branches enable the model to perform 2 tasks simultaneously: target localization, determining the precise position of the target in the radar data; target classification, identifying whether the target is a high RCS target, a low RCS target, or if no target is present. Finally, let's take a look at Figure 2, which shows the Python console during the training process. Here, the model is trained over 10 epochs, with clear progress displayed as the training unfolds. As we can see, the loss function decreases steadily, while the accuracy improves with each epoch. This demonstrates that the model is effectively learning to minimize error and make better predictions over time. At the end of the training process, the console also displays a confusion matrix. This matrix provides a visual summary of the model's performance in distinguishing between the different target classes. It shows how well the model can differentiate between targets with high RCS, low RCS, and the absence of a target, giving us valuable insights into its classification capabilities. This concludes the first part of the presentation, where we've explored the model's architecture, functionality, and training process in detail. Thank you for watching, and in the next part, I'll be diving deeper into additional features, results, and applications of this model. Stay tuned.